Hello, we're doing checkpoint 4.31. Here we're asked to build a fence along a stone wall, and let's say the stone wall looks like this, and this is your wall, and let's say you had a fence going around it, a rectangular fence. And so you want to build this fence with 200 feet of fencing, and what is the maximum area you can cover. So first of all, we're drawing our diagram and identifying some important variables that we might be using. So let's say we have x's and y, and we want to maximize the area, and so the area of this particular drawing here is going to be x times y. Okay, now we have a constraint. A constraint will give us a relationship between the two variables that we have. So right now a is a function of two variables, but we want a to be a function of just one variable so we can do the derivative and all that stuff. So let's identify a constraint. And the constraint is this fact that we have 200 feet of fencing. So if we add up x plus y, so that's 2x plus y is equal to 200. Finding this relationship between x and y will allow us to get this into just one variable. So if we solve for y here, for example, say y is going to be 200 minus 2x, then we can replace this function so that it's only a function of one variable x, and we can have x by itself, or x as it is, and then y is equal to 200 minus 2x. Now we have a function that we're trying to maximize, and it's a function of one variable, so we can certainly do the work that we need to do, like finding derivatives and things like that. So if we simplify this so that we can take the derivative a little bit easier, instead of using a product rule, we can just multiply out and take the derivative of a polynomial. So from here we would say a prime of x, and the derivative is going to be 200 minus 4x, and then we'll do the analysis, do the maximum analysis for this. This would be setting this equal to 0. So this is going to give us a negative 200 on both sides divided by negative 4. So x is going to be 200 divided by 4 is 50. Okay. So x is equal to 50. So now that we know that x is equal to 50, we should check that it is in fact a maximum. And we can do that by for me, I'll use a second derivative test. A double prime of x is going to be just negative 4, and that's less than 0, which means it's concave down. And so x equals 50 is a maximum. So now that we know that it is in fact the maximum, we can plug that to find the actual area. We just plug it back into the original equation, a of 50. So 50 is the length of this side, and so if this is 50 and this is 50, that's 100. Y must be 100 as well, because the fencing is 200, or you can solve for y here. So this would be 50 times 200 minus 2 times x. So that's 100. 100 times 50 is going to be 5 with a couple more zeros, so 5,000. So 5,000, this is feet. So we'll say square feet for your answer. So this is the maximum area. All right. One thing that we didn't do that we should have done is figure out the domain for the constraints. So the domain for x here, we need to know what values of x we can use. So the size of this thing will shift accordingly, but we essentially want our x value so that the relationship with a constraint and the other variable is going to give us something that would make sense, something that would be positive. So we can figure out the domain from here and saying 200 minus 2x has to be bigger than 0. And also x has to be bigger than 0. So this will give us 100, I believe. Y has to be 100, or the x value has to be 100. So x has to be 100. But it also has to be positive, so x has to be bigger than 0. We can keep it closed or open depending on how you view it, but if you put 0 in for x or 100 in for x, then you're going to get an area of 0, which is our degenerate case. But this will be our domain, and this is going to be our area, the maximum area. All right, I hope that helps.